Hello students, welcome to the class. Today's topic is uniform and non-uniform motion. So let's start. You could see that I have drawn some of the number lines. Okay, this is case 1, this is case 2, and this is case 3. Okay, students, let us consider in case number 1 that a body is here, okay, at 1 meter of distance from its origin. Okay, that means 0. Here 0 is taken as origin. Alright, so being an observer, you see that the position of an object, the position of a body at 0 second, at 0 second is 1 meter. This is the distance, this is the distance in meters, distance in meters. So being an observer, you see the position of a body at 0 second at 1 meter from its origin. Again, after 1 second, you find that this object is still here. In another second, again the position of object is here only, and finally again at 3 seconds of time you find that the object is still stand still right there at a scale of 1 from its origin. What do you observe here? You observe that by every passing of single seconds, the body is kept itself intact at the same position. So we could conclude that this position, okay, the body's position is, we could say that this is a rest position. Alright students, in case 2, now in case 2 we suppose that the position of body, okay, is at 0 meter in 0 second, 0 meter at 0 second. Okay, now in the next second, that means in 1 second, a body covers a distance and reach to the scale of 2 meter in 1 second. After a while, okay, in the second we find the position of a body is right here. Okay, when 2 seconds has gone by, in the third second we find the position of a body here at 3 seconds. All right, what are we actually observing? What are we noticing? What can we conclude out of this? We could conclude that at 0 second of time, the distance covered, or the distance or the body is at 0 meter. In the first second, the body covers a distance of 2 meter, and in the another second of 2 second, a body is reaching to a scale of 4 meter. In the third second, a body is reaching to another position at a scale of 6 meter. Okay, so everywhere, in every second, you could see that equal distance, if I will find that what is the difference between the distance, we will say here 2 minus 0. Okay, again here 4 minus 2, again here 6 minus 2. What is the resulting displacement or distance done here? 2 minus 0, 2, 4 minus 2, 2, 6 minus 2, 6 minus 4, sorry, 2 meter. Everywhere 2 meter of distance is covered. Okay, in a regular interval of time, 1 minus 0, 1. Okay, here 2 minus 1 gives 1, and 3 minus 2 gives you 1 second. At every single second 2 meter distance is covered. Okay, now in case number, okay, so here equal distance of 2 meter is covered in equal interval of time. 1 minus 0, 1 second, 2 minus 1, 1 second, 3 minus 2, 1 second. So such speed or such motion is called uniform motion. Uniform motion. Okay. Now come to case number 3. The suppose that the position of body is at a scale of here of 0 meter in 0 second. In 0 second. Okay. In the first second, the body is able to reach out to a scale of 2. In the first second, the body is able to reach out to a scale of 2 meter. Okay. In the second second, the body is reaching to a scale of 3 meter. We find that in the third second as well, the position of a body is at a scale of 3 meter. So we can see here that the distance, okay, distance covered is 2 minus 0, which gives you resultant as a 2. 3 minus 2, that is 3 minus 2, that is equal to 1 meter. Now here in we cannot see that there is any change in the position of a body. In the second second, the body is still right here at a scale of 3. In the third second as well, the position is here at a scale of 3. Okay, so such motion where unequal distance, here 2 meter, here 1 meter, unequal distance is covered in equal interval of time, 0 to 1, 1 to 2, 2 to 3. So such motions are called non-uniform motion. Non-uniform motion. Now let us see the graphical patterns that would they suggest here. Okay. Alright. So here I have prepared a graph, position time graph. Okay. So in the first case, the position of a body was 0 at 0 second, 0 meter at 0 second, that means this position. Okay. In the first second, the body is here at a scale of 2 meter. In the second, the body is reaching to a scale of 4 meter. In the third second, the body is reaching to a scale of 6 meter. Okay, we can see that these all points are collinear. Okay, so what are we going to get? We are going to get a straight line. So straight line is obtained in case of only uniform motion. Uniform motion. Okay, so this is the graph which is plotted against case number 2, condition number 2. Let's see that what sort of graph is obtained for case number 3, which is related to the non-uniform motion. Here we are having 0 meter at 0 seconds. So this is the first point obtained. Now in the first second, the distance covered is 2 meter. In the second second, the what we should call the position of body is still right there at 3 meter of scale. In the third second as well, in the third second, right, the position of body is right here. If we connect these points, what do we get? We get a curve line. Okay, so such curve line actually denotes the non-uniform motion. Non-uniform motion. Alright students, non-uniform motion. Now let us discuss the first case as well here in the graph. In the first case, we have seen that body position in the 0 second is at 1 meter. 0 second, this is 0 second, this is 1 meter. Alright, so this is the current point that we are going to obtain. In the first second as well, the position of a body is at a scale of 1 meter. In the second, again the position of body is at a scale of 1 meter. In the third second, we are having that same allocated point. Now if we draw this line, we get such plotting of the graph. So this shows that this is a body is at a rest position. Have you understood it, students? Alright, let's discuss one graph here. This graph. Now this is a sort of discussion which is supposed to be conducted for the elaborated way to understand the concept. Now here is the graph, you can see. Okay, this is distance time graph, position time graph, and we have been asked to determine that what is the position of a body in which context they are heading to. So from A to B, a straight line. Okay, so just now I have told that a straight line gives us indicates us that the body is at rest position. A body is at rest position. So A to B, the body is at rest position. Now B to C, this is a curve line. Can you see here? Yes, this is curve line. So we will say that this is non-uniform motion. Non-uniform motion. Now C to D is a straight line. Okay, look at this black line. All right, C to D is a straight line. So here in straight line, where, okay, in which graph, in which condition we get the straight line, we will say that must be having uniform motion. So this is uniform motion. Now D to E, again D to E, can you see this is the curve line. So D to E is non-uniform motion, non-uniform motion. And E to F is straight line. So straight line indicates about the rest position of a body. So we will say here a rest position. So this is understood, I guess. This much of the concept is necessary to understand the uniform, non-uniform motion as well as position of a rest body. Okay. Now the next topic is acceleration. Acceleration, as you can see the car, initially the car is standstill, having no velocity contained in it, so there will be no speed, so 0 kilometer per hour will be notified in the odometer scale, right, or speedometer scale, sorry. After moving, after a while, suppose 30 minutes of time has gone by, okay, sometime after some time a car is speeding up itself and reaching to the another speed of 40 kilometer per hour, okay. In the another 1.5 hour, suppose that 1.5 hour, finally the car is attaining its maximum speed of 80 kilometer per hour, okay. So what are we actually observing? We are observing that by by every passage of a time, within 30 minutes, the car has changed its velocity from 0 to 40, and in the next 1.5 hour, okay, the car is speeding its motion or changing its velocity from 40 to 80 kilometer per hour. So what is the key factor here? Velocity changing. Velocity changing. So velocity changing is of course a very key factor. There is another key factor. What is that? That is time. Without time span, none of the entity in this whole universe can change its velocity, okay, can come into motion. Okay, let's see the another one. As you can see that this body is at a position having 0 meter per second at time equal to 0 second, okay. After the passage of 2 seconds of time, the body is reaching to the another position of B, having the final velocity as 10 meter per second, okay. So what can we observe here, students? We can observe, of course, these two factors, right? Velocity changing and change in time. So students, this acceleration, acceleration is actually the change in velocity, not, it is not termed as change in speed, okay, because change in speed is a scalar quantity, all right, whereas acceleration is a vector quantity. So with respect to vector quantity, we'll have to name it as a velocity, not as a speed. So acceleration is actually defined as change in velocity with respect to change in time. Alright, so how much velocity changed? Here we will say that a equal to change in velocity. What is the final velocity that we have getting here? 10. What is the initial velocity at 0 second? 0. And what is the time span that we have gone by? We will say final time is 2 second and initial time was 0 second. So this is how we got that acceleration of 5 meter per second square. How? 5 meter per second square, how? Because 10 minus 0 is giving us unit of meter per second, and 2 minus 0, the unit of second, the unit of time is second. So meter per second by second gives you meter per second square unit for the acceleration. So what is the meaning of 5 meter per second square? Okay, suppose that a body has an acceleration of 5 meters per second square. Explain in your words what you will write. You can say that each second velocity of 5 meter per second is changing in that physical body. Once again I am repeating. What is the matter? The matter is, if it is said that define that a body is containing 5 meter per second square acceleration, what do you mean by it? What you will say? You will say that by each and every second the velocity of 5 meter per second is changing within that physical body. Okay, so this is how this expression comes. Which expression? A equal to change in velocity by change in time. So change means delta. So this is the sign of delta. Okay, so velocity means v. So delta v by delta t. So delta v is also can be expressed in this way: v2 minus v1, and delta t equal to t2 minus t1. Okay, let's understand some more concept about the acceleration. Okay, now here students, see, let's see here that this is the position of body, which is A, having speed of 10 meter per second at 0 second time scale. After 2 seconds also we find that the body is containing the same speed, right? So what is the formula that we have just gone through? A equal to delta v by delta t, that means change in velocity by change in time. So what is the change in velocity? 10 minus 10 by change in time, that means 2 minus 0, that means 0 by 2. What is the acceleration? 0 meter per second square. Okay, we must understand here that all acceleration which contains 0 meter per second square is known as constant acceleration, but it is not that much. It is beyond more than this. The concept is huge. Let's understand the another thing as well. The position of a body at A at 0 second having velocity of 2 meter per second. Now the body is reaching to the position B having a velocity of 6 meter per second in that next second. That means in the first second. In the first second, what is the speed which changed from 2 meter per second to, we will say, 6 meter per second. In the 2 second, the body is reaching from B to C position having a velocity or having a next change of velocity of 10 meter per second, right students? So here A to B, what is the change in velocity? We will say that 6 minus 2 gives 4 meter per second from A to B, and from B to C again 10 minus 6, again 4 meter per second, right? So acceleration is fixed now. Acceleration is fixed because in both the cases, from A to B and B to C, there is a constant velocity changing 4 meter per second in the first second of time, and again 4 meter per second at a scale of 2 seconds of time. So we will say that acceleration is 4 meter per second in every second changing, right? So this is also what? Constant acceleration, correct? Why constant acceleration? Because this is not changing its velocity. By the passage of every second time, it is not changing its velocity. So we have seen in one case that A is equal to 0 and this is a constant acceleration, and here we have seen that A is not equal to 0, despite that this is constant acceleration. Okay, alright students, now look at this third case. Now the position of body is A at 0 second containing 2 meter per second speed, velocity. In 1 second the body is having a velocity of 5 meter per second in position B. Now you can see that the same body is reaching to the another position of C, and in the second the speed is rising from 5 meter per second to 7 meter per second. So from A to B, what is the change in velocity? We will say 5 minus 2, 5 minus 2, which gives you 3 meter per second. From B to C, we will say 7 minus 5, which is 2 meter per second. Here 3 meter per second, the velocity changing in the 1 second, okay? In the another second, 2 meter per second is velocity changing. So these two are varying. The speed, the velocity is varying from each other. So such acceleration which keeps varying itself is called variable acceleration. Okay, what sort of acceleration? Variable acceleration. So that is why I have prepared a sort of chart to understand about the acceleration. So acceleration we can divide into two sort of things: constant acceleration and variable acceleration. Constant acceleration and variable acceleration. So variable acceleration is case number 3, and constant acceleration are of two types: when acceleration is equal to 0 and when acceleration is not equal to 0. I hope you have understood this much, students. Okay, equations of motions. The next topic is, the first equation of motion is v equal to u plus at, where v is final velocity, u is initial velocity, t is time, a is acceleration. Now this is the second equation of motion, s equal to ut plus half at square. So s is not distance here, s is displacement, t is time, a is acceleration, and half is just a fraction. Now the third equation of motion is v square equal to u square plus 2as. Alright, so here v is final velocity, u is initial velocity, a is acceleration, and s is displacement. Okay, in two ways we can derive these equations of motions. So what are the two ways? Number one ways is mathematical derivation. Mathematical derivation. Okay, and another one is called graphical derivation. Graphical derivation. So let us understand. So first of all, we will discuss about the mathematical derivation. Derivation means verification, proof. So first is b equal to u plus at. Alright students, so b equal to u plus at. So we can say here from the definition of acceleration, okay, or from the formula of acceleration, a equal to b minus u by t. Correct students? Now a can be written as a by 1. So by cross multiplication, by cross multiplication, we get what we get, b minus u into 1 equal to a into t, right? So b minus u into 1, that means b minus u, a into t, that means at. So b equal to minus u will be transposed to the right hand side, minus u will turn into positive plus u, right? So u plus at. So this is the derivation of first equation of motion. Alright, now students, the second derivation, let's see. What is the second derivation? S equal to ut plus half at square. Okay, alright. Now students, how can we derive? We will write that from the definition of average speed, okay, average speed or average velocity, what we can write, VAB equal to u plus b by 2. Correct? Let us consider it as equation number 1. Equation number 1. Now v equal to u plus at, just now we have proved it. Let us take it as equation number 2. Now on putting the value of v, okay, in equation 1, so VAV equal to u plus b. Instead of b, what we can write, u plus at by 2. So VAV equal to 2u plus at by 2. Okay, so VAV again can be written as 2u by 2 plus at by 2, that is equal to u plus half at. Equation number 3. Okay, alright. Now what is the formula for distance or displacement? We know that distance or displacement equal to, right, speed into time or velocity into time. So here the velocity is VAV into time. So S equal to VAV. Place this value of velocity. What is this value? U plus half AT into T. So S equal to U into T, UT plus half AT square. So this is the derivation for second equation of motion. Okay students, Now moving on to the last derivation for third equations of motion, and it is what? V square equal to u square plus 2s. Third equation, v square equal to u square plus 2as. Okay, this can be also verified by both the equation, either of the two. Either of the two means from first or second. So I am taking the first equation. We can write from the first equation of motion. We have v equal to u plus at. We write that on a squaring both sides. So this becomes v square equal to u plus at whole square. This gives you a square plus 2ab plus b whole square. So b square equal to, so u square plus 2uat plus a square t square. Okay, so v square equals to u square plus 2a. I am taking it as a common. So if I take 2a common, what will be the leftovers? You will say that ut plus half at square. How half? Because this is 1. If nothing is there, so 2 into half, can it make 1? Alright. And a one acceleration term is taken as a common, so 1 is kept inside, so half at square. So v square equals to u square plus 2as. So this is the third equation of motion, students. Okay, thank you. That is it. This is it.